So for my second lecture, I'm going to first continue the discussion we were having about LIGO sources and what we can learn from the observation of gravitational waves, which parameters gravitational wave detectors are capable of observing. And then we'll look a little bit at what LIGO has actually observed so far before moving into how we actually do simulations of these systems on the computer. So let's start with finishing what I was talking about at the end of the last lecture, which is which binary parameters can detectors such as LIGO and Virgo accurately measure for different signals. What we saw last time, yesterday afternoon, was that the best measured parameter for LIGO is that chirp mass, which is something that you can derive just by equating the amount of energy lost to gravitational waves with the change of energy of the compiled binary of the two black holes. And we derived this yesterday, that the fact that there is a not so simple, but there is a relationship between those three parameters here: the chirp mass, the time derivative of the gravitational wave frequency, and the gravitational wave frequency itself, which sets the leading order behavior of the system. So this chirp mass is really what LIGO to zeroth order is capable of measuring, and what LIGO can pretty much measure for any signal that it observes. Now we would like to go a little bit further and detect individual masses of the object. And you see here that even though in the direction orthogonal to the chirp mass, the determination of the masses is not great, there are still some constraints that exist here. For example, the masses of the most massive object here is limited to somewhere between 1.3 and 2.75 solar mass. It's not a very great measurement, but it's some constraints. It's not just the chirp mass. And there are multiple ways in which you can get additional information. Here I'm showing you a gravitational wave signal, which comes from a black hole neutron star merger simulation, but it doesn't really matter here whether it's a black hole neutron star or a black hole. This is a higher mass ratio system. So it's the most massive object is 7 times the mass of the least massive object, which in this case is the neutron star. And we can see whether the gravitational waves look different from what we were seeing for equal mass system. And the black curves here shows you what happens if the system is seen face on, so if the orbital plane of the binary is orthogonal to our line of sight. Right? And there are no real features to the gravitational wave signal that look different from when you were seeing an equal mass systems before. On the other hand, if you see the system edge on, so if the line of sight to the binary goes through the orbital plane of the binary, then you see that one of the polarization, the one at the top, the H cross polarization, is 0. We don't see anything in that polarization for an edge-on system. And the other one shows some oscillations at higher frequency. And that's from the fact that depending on whether the small object or the big object is passing in front of you, you get more or less gravitational waves. So you have an additional higher frequency signal that comes in, which can give you some information about the mass ratio. So that's one thing that you can use to measure the mass ratio, is those changes of amplitude, or the fact that there is higher frequency modes that are detectable in gravitational waves. It's not very easy for LIGO to do, because LIGO is mostly sensitive to the main phase of the signal, not so much to the amplitude. And so that's a bit of a complicated measurements for LIGO to make. The other way in which you can measure that mass ratio is by continuing the expansion around Newtonian physics. And I'm not going to do it because it becomes very complicated very fast. But if you do the next order expansion, which is called the first post-Newtonian approximation, which is basically a correction to what we have seen for the chirp mass of order v square over c square. If you actually include that term, then the mass ratio comes into play, not just the chirp mass. So then if you can measure that second term, that second order term, that first order correction, sorry, then you can actually measure the individual masses of the two objects. But even at merger, this is only a correction of 20 or 30% to the energy budget of the system. And far away from merger, it's only a few percent, maybe, or even less. So this is a very hard things to do if you don't have a long signal to use in a high signal-to-noise ratio. And the other thing that we can see from here is that with polarization information, so if you have two polarization of the gravitational waves, you're starting to be able to get information about the orientation of the binary, whether the binary was face on to us and orbiting this way, or whether it was edge on and orbiting this way, compared to you. And so, because if you have polarization information, you can see whether both the amplitudes of both polarizations are similar, or whether they are very different, which would tell you that it's edge on. So with multiple detectors that have different orientation, you can start to get better information about the orientation of the binary. And that's particularly important if you are thinking about neutron star mergers and gamma ray bursts, for example. We've heard a few talks already mentioning how important it is to actually get some information about the orientation of the gamma ray bursts with respect to us. If you can get information about the orientation of the binary itself, that helps you with that kind of determination. All right, so that's for the masses. So you measure the chirp mass at 0th order, and then if you can capture the v square over c square correction, the first correction, you can get the individual masses. If you want to go further than that, the next thing that we would like to measure with these gravitational waves is the rotation, the spin of the black holes. And again, that comes at even higher order in the expansion around Newtonian physics. The largest effect that you can see from the spin of the object is something that is not really intuitive. It's something that only exists in general relativity. And it's the fact that if the two black holes are spinning in the same direction as they are orbiting each other, right, if the spin of the black hole is aligned with the orbital angular momentum of the system, then they inspiral slower. They stay for longer at a given separation and inspiral slower towards merger. If, on the other hand, they are anti-aligned, so they are counter-rotating with respect to their orbital motion, they inspiral faster. They spend less time at a given frequency. This is shown here. This is a mass ratio 3 system, but that doesn't really matter much. The red curve is for non-spinning black holes. The blue curve is what happens if the black holes are co-rotating with the orbital motion. And the light green curve, I guess, are for black holes counter-rotating with the orbital motion. And you can see that the counter-rotating ones inspiral and merge faster than the co-rotating ones. Sorry, the yellow curve was the one with anti-aligned black holes. The green and magenta curves are for one spin aligned, one spin anti-aligned. And the magenta one is the one where the most massive object is co-rotating. So this effect, which wasn't really necessarily expected, but it can be derived in post-Newtonian theory, and it can be seen in numerical simulations. It's just something that you wouldn't expect from Newtonian physics. This effect can be measured, but it's an even higher order effect. It's a v cube over c cube effect. So again, you need even longer waveform, better signal if you want to extract it from your observations. And that allows you to measure one component of the spin. So one of the 6 parameters determining the rotation of the two black holes. Each black hole has a spin magnitude and orientation. So there's 6 parameters total. This allows you to measure one. So there's one best measure spin parameter that LIGO can hope to observe. And that's the only one on which LIGO so far has managed to put any significant constraint with observation, as we will see. And then if you want to go further than that and actually determine the other components of the spins and their orientation, then you have to rely on even higher order effects. And the easiest to see is the precession of the system. So you can imagine if I have a black hole which is spinning, but it is not spinning, its spin axis is not parallel to the orbital angular momentum of the system. It's misaligned. So you end up with something like this. It's too bad there is not a pointer. the total angular momentum is the blue arrow here. So the orbital angular momentum is the blue arrow. The total angular momentum of the system is the gray arrow, and the spin are the red ones. And as the system evolves, total angular momentum is going to be more or less conserved up to gravitational wave losses, but that occurs a fairly long time scale. But the individual momenta, the orbital momentum and the spin momentum, are going to precess around the total momentum. So if I have my total angular momentum and my orbital angular momentum, the orbital angular momentum is going to precess around the total angular momentum. And the spin is going to do the same thing. And what this means is that your orbital plane is going to precess over time. It's going to change orientation over time as the orbital angular momentum precess. And similarly, the spins are going to precess over time. So the orientation of the binary, because of that misalignment of the spin, is going to change over time. And because the orientation of the binary changes the amplitude of the waves in different polarization, you are going to end up with that kind of modulated signal, which sometimes the binary is seen nearly face-on, sometimes it is seen nearly edge-on, and that modulates the amplitude of the gravitational wave signal. What
sets the precession time scale?
It's the magnitude of the spin and the orbital angular momentum, and then some prefactor that depends on the masses. But effectively, it's what the effect of frame dragging from the spin of the black hole is if you in general relativity. But it's sorry.
So it's order seconds near the inspire.
It is of the order close to the merger of 10 or tens of orbital period if you have maximally spinning black hole.
Okay.
So close to merger, maybe it's 100 milliseconds, but it gets longer as you get farther away from merger.
Okay, because it scales it's like omega length theory, which goes.
Kinda, yes, yes. It has terms of that type. Yes, okay. Exactly. Yeah. Yeah. So far away, it's a pretty slow thing, and if you see close to merger, the modulation becomes faster. Even relative to the orbital motion actually itself. There's also a contribution to the phase, but it comes at even higher order, so V4 over C4 now, which makes it even harder to measure. So that's something that LIGO might be able to see in the future with higher signal-to-noise events, but that it hasn't been able to see so far. We will see that there is basically no constraint on the precessing component of the spins in LIGO measurements so far. So all of that was for the inspire of the objects, which I've tried to put in the context of at which order in expansion around Newtonian theory it comes in, and that's really only a concept that is valid if the objects are well separated. Close to merger, post-Newtonian theory, expansion around Newtonian physics does not work because general relativity looks very different from Newtonian physics. So you have extra information in your gravitational wave signal, which comes from the merger itself, which actually has a lot of energy in gravitational waves. And the merger itself, this is the merger of, again, mass ratio 3 black-hole binaries. The merger itself is going to give you information which is more closely related to the total mass and total angular momentum of the objects, and especially the post-merger information. So as the black holes collide and form a single black hole, a single horizon, that black hole is going to be very distorted initially. It is not going to be a stationary Schwarzschild or Kerr solution. And then it rings down by emitting gravitational waves. And that ring down is a combination of all the excitation modes of the black hole. But pretty quickly, you are left with only a few of the least damped modes that contribute to that signal. And the frequency of those modes depends on the mass of the black hole. So the merger signal and the spin as well. The merger signal is going to be, and especially the post-merger signal, is going to be more sensitive to the total mass and the total angular momentum of the system rather than the chirp mass. So that's another way in which you can disentangle parameters is that if you are capable of seeing the post-merger signal, then you get information about the sum of the two masses instead of that weird combination of the masses that is the chirp mass. All right, so that's what we have at our disposal from a physics point of view, what we expect LIGO to be able to see. So let's look at actually what LIGO has seen so far and try to put that in the context of what we have just discussed. Unless there is any question on the parameter determination part first. Yeah.
Is it true that when the two black holes merge, that they're always going to be the sum of the two masses?
Not exactly the sum of the two masses, because some of the energy is lost to gravitational waves. So if you consider the masses when the black hole were very far apart, and the masses of the final black hole, the mass of the final black hole is less than the sum of the two masses. But it's less by a fraction that you can predict from numerical simulations of gravitational waves, because you know how much energy is lost to gravitational waves. And it's from a few percent to a bit more than 10% if you have really a rapidly spinning black hole, because they spend more time orbiting each other, they lose more energy. So between a few percent to maybe to a bit more than 10% of the mass is lost to gravitational wave emission, and then the rest remains in the final black hole. And it's similar for the spin. It's rough. It's whatever the total angular momentum of the system was minus what is lost to gravitational waves. But there you lose a larger fraction to gravitational waves. That makes sense? Anything else? Okay. So this is a plot that many of you have probably seen in talks before, which is the first detection of gravitational waves by LIGO, which was in September 2015. All of those GW 150914, it's gravitational waves and then the date. And that's it. And so far, we haven't had the chance of seeing more than one gravitational wave in a day, so there hasn't been a need for any addition to that nomenclature. But maybe one day. So what you see here at the top is what the signal looked like more or less in the detector after you clean up the low and high frequency part of the signal where there is a lot of noise. But that's all you need to do for this signal, which is very, very bright as far as gravitational waves are concerned. And the way LIGO goes about detecting a signal is by comparing with a large bank of gravitational wave templates, which come from, in part, analytical methods such as the post-Newtonian expansion, and in part by calibrating models to numerical simulations. We can't use numerical simulations because LIGO needs to go very fast computing models. Numerical simulations, on the other hand, takes months to do one configuration. And so we can't use numerical simulations directly to do LIGO data analysis. But we use analytical models that are calibrated to the results of numerical simulations and match the numerical simulations well enough. And we'll see what well enough means in a minute. But so LIGO is going to compare to a large number of gravitational wave templates and figure out which match the signal reasonably well, if any. And that's the second line that you can see here is the best fitting model for the gravitational wave from a template bank of theoretical gravitational waves. And this gives us an idea at least of what the best parameters are for the merging objects, because each of those templates corresponds to a certain mass of the more massive black hole, mass of the smaller black holes, and spins of the objects, and so on. So we can get an idea of which parameters are possible for this given event by seeing which of those templates actually match as well. And then LIGO, after that, after detection, goes through a much more in-depth analysis of the signal to actually precisely determine the parameters, where they use a lot more templates and actually do an error analysis to see what the errors are on the individual parameters. That's a much more complicated process. But for detection, you just need an analytical signal that reasonably matches the reality. And the fact that it matched an analytical waveform was already a very big success for this first event, because this actually means that the waveforms that were produced assuming that general relativity is correct actually match what LIGO saw for the merger of two black holes. And there was no guarantee that this was going to be the case, because this is the first time that we could observe general relativity in the nonlinear regime with two objects merging with each other. So the fact that actually, yes, the signal matched the theoretical predictions was already a pretty big result in itself. Should add that this is actually also the only LIGO signal so far that would have been detected even if we had not known what the signal was before. This one was also detected by a search method that does not assume a given signal. So if general relativity had been wrong and we had seen this black hole anyway, we would have known it. We would have detected the black hole and then see, oh, it doesn't match any of our signal. And then maybe we would not have believed it. But that's another question. But we would certainly have had an event which would have looked very weird to LIGO if two black holes like these had merged and general relativity had been wrong, sufficiently wrong. There was a question yesterday about the noise curve of LIGO, the actual noise curve of LIGO. So this is what it looks like at the time of detection when you take the real noise curve and not the idealized ones that I showed you before. So you can see there are a lot more of those lines that comes from various features of the detector, suspension, resonance of different subsystems of the detector. So it is not a clean noise curve as we have seen in those idealized design plots. There is a lot more features that comes in, but overall it has the shape that you would that you predicted when you made the design of LIGO. So that was the noise curve of LIGO at the time of the first detection.
How much sky coverage are we going to have once? So you were showing all the detectors yesterday. So once they're all online, how much coverage?
You get full sky coverage.
You get full sky.
Yes. Not all directions are equal. So you can see farther in some directions than others. But you are sensitive to, you are reasonably sensitive in all directions, especially once you get either Virgo at design sensitivity or Cagra, then you can go reasonably far in all directions. Currently Virgo was a bit more noise than LIGO because of suspension issues, so it doesn't see as far. But the sensitivity is still dominated by the LIGO sensitivity, which is very asymmetric there. It has blind spots. But once Virgo has its suspension is upgraded, or once we get Cagra online, then you get pretty much full sky coverage for the for gravitational waves. So one question that we can ask ourselves with LIGO is, how does LIGO check that a signal is actually real? We have mentioned that LIGO is a very high precision experiment. It needs to really accurately measure changes in the length of the arms of the detectors at an accuracy where any sort of local perturbation can mimic a gravitational wave signal. And that means that you need to see something at least two detectors to believe it. And practically, the way you check that you have seen it in two detectors and it is not random luck is with studies such as the one shown here. And what is done is that LIGO takes, this is the first detection, so there was only LIGO, there was no Virgo. You look at the signal in the two LIGO detectors, and then you take, let's say, Washington, and you say, I'm going to shift the signal by 1 second. And it takes light, if I remember properly, 7 milliseconds only to go between the two detectors. So a signal which is seen in two detectors 1 second apart is certainly not physical. It's too much of a time lag. At most, they can be separated by 7 milliseconds. So you make those shifts with multiple time shifts, and anything you see once you have shifted the signal is coincidence. It's noise. And you can see what kind of signal to noise you get for those random fluctuations of the noise in the two LIGO detectors. And those are the green and black curves on the left and the black and blue curves on the right. These are for the two different searches. The one on the left is the one that doesn't assume a specific waveform. The one on the right assumes that we know what the waveform looks like. You can see that there are a bunch of events, those orange squares, which are on the left, where the number of events expected just from random fluctuation of the noise is about between 1 to 0.1 in that data, which is about 15 days of LIGO data at that time. And an event which had a 10% chance of happening by chance is not something that LIGO was going to use to claim a first detection of gravitational waves. It's especially as noise modeling comes with uncertainty, so maybe it's not 10%, maybe it's actually 50%, maybe it's 1. We don't really know for sure. But on the other hand, the actual event that was claimed, the one all the way on the right, is so loud that they couldn't find a single coincident event that had the same noise, that had the same signal to noise, just from random fluctuation of the noise. There is absolutely nothing in the black or blue curves that goes all the way to the signal to noise of about 23 that event had. So actually, it is so loud that at the time at which they made their detection, they couldn't say what the statistical significance of the event was. They didn't have enough data to actually figure out what the statistical significance was, just that it was more than 5 sigma, which is, they waited long enough to get that and they'd say, okay, we have a detection. And then later on, they were able to say that it's a lot more than that, but that doesn't matter by that point. So this was an extremely loud event, so loud that they couldn't even figure out how unlikely it was to happen by chance. It's not quite 5 sigma. Actually, on this part, it is not 5 sigma on the agnostic search, the one that doesn't assume a waveform. But that's, again, because there wasn't enough data. Nowadays, with all of the data from the first round of LIGO observation, even that pipeline finds a more than 5 sigma detection. So it would have seen it, even if it had not been a gravitational wave signal that was in agreement with general relativity. The only assumption made in the left side is that the frequency increases over time and the amplitude increases over time. So maybe you can find a weird theory of gravity that doesn't do that, but it's hard. All right, so LIGO has seen more than one event. Actually, it has even seen more than those 4. No, it has seen 2 more than that. But we can see the range of events that LIGO can see in this plot here. So in your opinion, which of those events should be the one with the highest mass black holes, you think? Just by eye, we should be able to actually say that. First one, the one at the top, yes. Because it is shorter in the detector. The detectors caught it later in its evolution. So that means that the masses are higher. It could also mean that the signal is much lower signal to noise, and we only saw a very small bit of it. But that's not what is happening here. And of course, the lowest mass system is the longest one for the same argument. Now, you can also think, which ones are going to be best to do what? The first signal, which is the most massive, is going to be best to measure individual masses because we have the pre-merger and the post-merger signal. Well, the longest one is going to be the best to measure the spins of the object because we have a much longer its spiral and we can disentangle all those post-Newtonian terms from each other. So GW150914 is the one that gives the best result for individual masses, but 151226 is the only one for which we actually measure some spin. We will see that. Another thing is for test of general relativity, the first one allows you to very well test consistency between the pre-merger and the post-merger signal in general relativity, while the longest one allows you to test post-Newtonian theory better, but doesn't give you much information about the merger because the merger is at high frequency where LIGO is less sensitive. So all of those observations, and we don't have that many so far, but we'll have more in the near future, all of those are complementary and provide you with different kind of information about the merging objects. This is the ones that we have actually seen so far. So here we have all of them. It shows the masses of the objects again, the blue events here are black hole mergers seen by LIGO, pre-merger and post-merger masses. And you can't really see the error bars, unfortunately, at least I can from here. I don't know if you can from above. But the error bars of the mass are a lot lower for the high mass systems than for the low mass systems. Yeah, it's hard to see. But for example, for the lowest mass system, the fourth, I guess, from the left, the error bars go all the way from 5 to 10 solar mass. So you have a factor of 2 uncertainty for the lowest mass black hole. And that's because you only really measure the chirp mass very well for that system, but you don't do very well at the individual masses. The other thing to note is that the purple circles here are black holes that are observed in the Milky Way, not through gravitational waves, but through electromagnetic signals coming from the accretion disk. And you see that, generally speaking, the population of black holes seen with LIGO is more massive than the population of black holes seen in the Milky Way. But there is one important bias to keep in mind for that, is that LIGO, the amplitude of the gravitational wave signal scales with the total mass of the system. LIGO is able to see a 60 solar mass system about twice as far as it can see a 30 solar mass system. And because LIGO is sensitive to the volume of space that it can see, a 60 solar mass system can be, is 8 times more likely to be seen than a 30 solar mass system. If they have the same event rate, you will see 8 times more 60 solar mass system than you see 30 solar mass systems. So the fact that you have seen 2 or 3, let's say, relatively high mass black holes and then 2 low mass black holes and 1 in the middle, that doesn't mean that there are more high mass black holes. It just means that you can see them much farther. So maybe there is more high mass black holes in cosmological scales than there is in the Milky Way. That's perfectly possible. But we will have to figure out what the biases are in all those observations before being sure. And it's the kind of thing that is hard to do, the kind of statistics that is hard to do when you only have 5 or 6 events. And that's the kind of thing that LIGO will be very good at doing in the next few iterations of the detectors, starting next year, when it's going to see a lot more binary black holes. Then you will actually have a population of systems. The one at the bottom is the merger of 2 neutron stars, which we'll talk about a lot more later in these lectures. So that was the masses of the system. For the spins, as I mentioned, most of them, we have basically no useful information. It's all consistent with non-spinning black holes. For most of these systems, there is a constraint, which is like the spin was less than 90% of the maximum possible value for a black hole. It's not a very strong constraint. But the longest waveform, that GW151226, the one in December 2015, that one has actually an actual constraint on the spin. And this is shown on this plot where on the left, the vertical axis gives you the component of the spin which is responsible for that hang-up effect, the change in the rate of inspiral of the object. So it's the aligned components of the spin combined over both objects. And the horizontal axis is the leading order effect leading to precession, which is harder to measure. You can see that the effective spin for the aligned component, the one on the horizontal axis, is reasonably well constrained to being between 0.1 and 0.4, something like that. While the precessing component of the spin is basically unconstrained. In each of those plots, the green curve shows you the prior distribution that was used to do the search for the parameters, and the black curve shows you the posterior distribution of the search. So if those two are very similar to each other, it means that we basically had no information about what the spins were. If they are very different, it means that there was actually useful information in the data. Yeah.
Can you find the spin in the final black hole?
You have actually a pretty good idea of the spin of the final black hole. But it doesn't come from the actual observations. It comes from the fact that numerical simulations have told us what the result of the merger of 2 black holes is. And so we know that those black holes have actually a pretty high spin, somewhere between 0.5 and 1, depending on the mass ratio and orientation of the pre-merger spins and whatever. But they are expected to be relatively high spin objects. compared to what we observed pre-merger, certainly, where it seems like the spins are not that high. So yeah, we have constraints, but I wouldn't say that they are direct measurements of the spin of the black hole. They are predictions from simulations that nothing has shown to be wrong so far. And on the right here, you can see the individual spins of the two black holes. So that's the best that LIGO has been able to do so far. You can see that for the most massive black hole on the left, so the radius of that semicircle gives you the magnitude of the spin. The orientation is how misaligned it is with the orbital angular momentum. You can see that it is probably a non-zero spin, not certainly in this case. And it is most likely slightly misaligned, but still consistent with being aligned. So there's a slight preference for misalignment, but not great. The small spin, we can't say anything. It's basically, the distribution is all over the place. We have basically no information about what it was. That's not surprising. It's because we can mainly measure, one, if we were lucky, maybe two components of the spin, but it's very hard to go further than that. And we already saw this yesterday, but another thing that LIGO can do is give us tell us where those black hole mergers are happening, and that's interesting if if you wanted to know which galaxy it was happening in, let's say, but that has been very difficult for most of the events that we have had so far, because we only had LIGO for 4 of these events, and so as we discussed yesterday, the error bars on these observations are very large for the localization in the sky. It's only when we get Virgo online, that the error bars decrease. And they would decrease even further if we had Kagra or LIGO India. Both of them give a much better constraints on the localization if combined with LIGO and or Virgo. Okay. So that's what we have been able to say about the properties of the individual objects. We are starting to get a good idea of the population of masses in these LIGO observations, and that's very useful if you want to do astrophysics with these observations. You can actually constrain what is the population of black holes that we see in the universe. And that can tell us a lot about all the processes that lead to the formation of a black hole, such as core collapse supernovae, which Philip is going to talk about later this week, or also all the complex interactions between massive stars in binary systems, which play an important role in the formation of these compact binary black holes. For example, phases in which the envelope of a star engulfs the other star, and the two evolve jointly with a common envelope. That's a very complicated part of the evolution of a binary system to model, one which we don't understand very well, and one which has a lot of influence on which stars lead to black hole mergers and which stars do not. And once we get more of a handle on the population of black hole masses and spins with LIGO observation, we will be able to actually understand the astrophysics a little bit better. The other thing that we can try to do is get a constraints on general relativity. And I would say that those constraints come, broadly speaking, in 2 types of categories. There is consistency check, which just verify that what we observe is what we expect. And if it's not, then we better explain why. But so far it has been what we expect. And then there is more quantitative check in which you parameterize in some way deviations from general relativity and see whether a small deviation from general relativity is more or less consistent with the data than what we observe. Those are 2 examples here made by LIGO recently. The one on the left is a check that for the most massive system, the first one observed, that the masses that you infer from the pre-merger signal and the mass that you infer from the post-merger signal are roughly consistent. And so you can see at the top the mass and spin that were inferred from the inspired and from the post-inspired signal, as well as from the full waveform, which is IMR on this plot. And you can see that all 3 are broadly consistent, at least. This should actually answer better your question about the ability of detecting the spin in the post-merger. This is the only signal for which it is possible, the most massive one. You see, it's The spin part is not great. It's between 0.1 and 0.9 if you marginalize over the spin. And that's the only one for which there's any information. The mass is better. On the right, you can actually try to measure the Poisson coefficients by looking at the in-spiral signal and compare them with what you would expect in general relativity. You can constrain them to relative errors that are shown here for the best ones of order 10%, for many of them, at least of order 1. So, not amazing, but still a constraint that did not exist before. And then if you go to very high order, then you basically lose any constraining power over the coefficients. And for that, it's good to combine both some very massive black hole observation and some low mass black hole observations, because they give you information about different aspects of the evolution of the system. Right? And so that's what is done here. This combines the most massive and the least massive signal of the first round of LIGO observations to get better constraints. And a third test of GR that was done is to try to determine whether the graviton has a mass. Meaning, if the graviton had a mass, then low-frequency gravitational waves would propagate at a speed different from high-frequency gravitational waves. And so you should see a distortion of the signal with waves of different frequencies traveling at different speed to you, and so arriving at different time. Right? We don't see that, and so you can put a limit on the mass of the graviton, which is comparable, which is at least comparable, if not better, than other direct, equally direct measurements. Also, there are some more model dependence measurements that are actually orders of magnitude better. This is not anymore the best constraint on the fact that gravitons propagate roughly at the speed of light, because the neutron star merger now gives us a much better constraint from the fact that the gamma ray bursts coming from the neutron stars and the gravitational waves arrive within 1 second of each other, roughly. And that's 1 second for a system that was 100 million light years away. So the relative uncertainty in the speed of propagation of gravitational waves with respect to light is 1 second over 100 million years, which is a much better measurement than anything possible with black holes. So that's some of the things at least that LIGO has been able to do with these first rounds of observations. What is coming up now is, well, there will first be a third run of LIGO observations in 2019, probably with upgraded lasers, at least in one of the detectors, which will give you higher sensitivity at high frequency, and most likely also higher sensitivity at low frequency due to improved seismic isolation. And I say most likely because they had issues in the second round of LIGO observations with the low frequency part of the noise. They think that they have figured it out, but they will only know for sure when they turn on the detector. And so they are really hoping that they are correct, because then you get a lot more ability to measure things like black holes, because a lot of the signal to noise is accumulated at low frequency. So you get a lot more events if you increase the low frequency, if you decrease the low frequency noise. The high frequency noise gives you better sensitivity to the mergers, which is also nice. Virgo should also be taking joint data with LIGO in 2019, at least at some point during the runs. So that will give us still a good sky localization during that run, which would be very nice if we see more neutron stars. And then there will be more detectors coming up in coming years, like CAGRA and LIGO India. We have seen black holes. We'll see that we have seen one neutron star merger. We hope hopefully that we'll see a black hole neutron star merger in the next few years. And from what we have seen so far, we expect we'll see a very large population of black hole mergers and neutron star mergers in the coming iterations of LIGO. Design sensitivity a few years from now, roughly speaking, LIGO should see about one event a week. There is an order of magnitude uncertainty in that number. And a bit less neutron star merger, maybe a 4 to 10 a year or so.
How long is the observing run in
It is supposed to be 9 months, I think, in the original plan, but they change that regularly depending on how the detector is doing and what they want to do to improve it. So it's never a firm commitment to that. They might change it. I think they've delayed the start of the run now because they were trying to figure out those low frequency noise and upgrading their lasers. And so I don't know whether it's still going to be 9 months when they start or not, and I'm not sure that they know themselves at this point. But that was the nominal duration of the 03 run, so the third observing run. It went from 3 months to 6 months to 9 months, and then it's going to be a year, I think, after that. And then we will see that with neutron star mergers, we can also do a lot of additional astrophysics, like understanding the enrichment of the universe in heavy elements and understanding gamma ray bursts, maybe. Okay. So that's what I wanted to say about LIGO observations. So if there's any other questions about the early LIGO results, going to take questions now. Otherwise, I'll switch to LISA and then numerical relativity. Okay. So there were a few questions about LISA during yesterday's lecture. So I tried to get a bit more information to answer them. I'm not a specialist on LISA science, so I just went and read their proposals. But I can hopefully answer at least some of these questions. So as a reminder, LISA is a constellation, as they call it, of 3 satellites, which is going to follow the Earth about 20 degrees behind the Earth in its orbit around the Sun. And in the latest iteration of LISA, but that changes occasionally depending on whether NASA is willing to put money in LISA or not. Currently, LISA is mostly funded by the European Space Agency. Currently, it's arms of detectors which are about 2.5 million kilometers. Right? And LISA rotates around the Sun and changes its orientation over time as it goes around the Sun. Right? And what it's sensitive to is all of these systems here. So we can't see, unfortunately, the blue dots. There are a lot of small blue dots which are supposed to be around the blue stars in the middle. Yes?
Just out of curiosity, are we going to be able to see like 3 dots in the sky at night?
No. There isn't much diffraction in the lasers would have to lose a lot of power for you to be able to see the laser beams shot from the... They are very far. They are like a month behind us in orbit. They are very far behind and pretty small spacecraft. I mean, imagine what the distances are here. They are months behind us on the orbit of the Earth around the Sun. They are not really close by. You can barely see something like the space station or satellites passing above us. You take a satellite of about the same size and you put it a month behind us on the orbit. You won't be able to see it. Right. So the main thing that LISA is sensitive to is those big blue stars, which are normally surrounded by a lot of blue dots, like thousands, but unfortunately the contrast here doesn't allow us to see it. And those are galactic binaries. They are mostly white dwarf systems that LISA is going to be sensitive to. They are not the main science goal of LISA, although LISA will be able to do some interesting science with white dwarf binaries. But they are there, and they are going to emit gravitational waves that LISA will see. And actually, their combined effect is what leads to that bump in the noise curve, the dashed line here, at around 1 millihertz or so. That's because of confusion noise from all of those binaries. LISA hope that they can reduce their noise and remove all of those binaries from the signal down to there, but not further. Other things that you can do are very massive black hole binaries. So those are the yellow and red and black curves that go across there and last from months to years in the LIGO data, in the LISA data, in the LISA signal, sorry. Those are 10 to the 5, 10 to the 6, and 10 to the 7 solar mass black hole binaries going from bottom to top. So that's the kind of equal mass black hole binaries that LISA is sensitive to. The light black curves on the right those are LIGO binaries that LISA can be sensitive to a few years before they get into the LIGO band. So those are the binaries with which you could do joint LISA and LIGO sciences if they were there at the same time, or LIGO a few years after LISA. And then the light red curves are extreme mass ratios. So that's what we were discussing yesterday, the plunge of a 1 or 2 solar mass object into a million solar mass black hole. Those are those light red curves here that Lisa would also like to see, because those actually allow you to do very precise measurement of the curvature around the massive object. Effectively, the small object acts as a tracer of the curvature of the big object. And it spends a lot of time at any given separation, and so you can get a lot of information about the curvature of the big black hole and its properties. So those are very good to test general relativity, or at least the part of general relativity that concerns a single black hole spacetime. All right, so that's the kind of science that LISA is capable of doing. And we had a few questions about the main sources of noise in this detector. And below about 30 millihertz, so the downward going part of the noise curve here, what limits you is spacecraft technology and our knowledge of the gravitational potential of the solar system. It's our ability to know what should a free-falling mass be doing when it is following the Earth a month behind, and how well can we maintain a spacecraft in free fall, and how well can we monitor the distance between the spacecraft. And most of that has been demonstrated to the accuracy required by LISA by the one satellite, LISA Pathfinder, that took data a year ago or so. So that part has actually been largely demonstrated. The technology required has been demonstrated. But that is what is limiting you at low frequency. It is a combination of being able to know what free fall means and spacecraft technology to actually maintain a free-falling mass in place and monitor distances between spacecrafts. Above 30 millihertz, so in the rising part of the noise curve, what is limiting you is the fact that the gravitational wave, the period of the gravitational wave, is becoming shorter than the time that a photon spends in the detector. Okay, thing. The length of the detector is 3 times 2.5 million kilometers, so about 7.5 to 10 to the 6 kilometers, which is 40 milliseconds of light travel time. So if the gravitational wave period becomes shorter than 40 milliseconds, no, one photon, as it goes around the detector, actually experiences a full period or more of the gravitational waves, and that actually decreases your ability to do interferometry with this object, because instead of assuming that one photon as a path which is affected by the gravitational wave at a given time, no, over the path of the photon, the length of the detector actually oscillates. And that makes things a lot harder to measure. So that is what is limiting you at high frequency in this case, is the fact that the frequency of the gravitational waves is too high, and so your photons are spending too much time in the detector compared to the gravitational wave period. And another thing that I wanted to clarify, we discussed a little bit source localization with Lisa yesterday. And Lisa is bad at doing localization if you have a short signal, if you see something for only a few days. But because the detector is actually rotating around the sun and changing its orientation, it can actually get very good localization if it gets a much longer signal. And most of the Lisa signals, actually last weeks to years. And so for those, Lisa is capable of getting good sky localization because it itself gets multiple polarization of the gravitational waves as it rotates around the sun. So the localization, it depends on what kind of signal you are looking at. But for many signals, it will actually be pretty good at localizing sources. Right. Any question on Lisa? Okay. So I'm going to completely change topic now and look at numerical relativity. How much time do I have here? 20 minutes, roughly? 20 minutes? Okay. Okay. So I'm going to start on numerical relativity, and we'll probably finish that and then switch to neutron stars this afternoon in the third lecture. So one of the main motivation at the moment to do numerical relativity, which is evolving Einstein's equations on a computer, is to provide LIGO with those model waveforms. As I said, not directly using simulations to compare to the LIGO signal, but at least use them to calibrate analytical models. And that's because LIGO relies on accurate analytical models to do its parameter extraction, as we have just discussed. You can ask yourself, okay, what does happen if you do not have a sufficiently accurate model? And there are two consequences of that. One has to do with detection, and one has to do with your ability to measure parameters of the binaries. For detection, you want the overlap between the two signals to be high enough so that when LIGO does its matching between the signal and the model, it gets a sufficiently high value. And if you start to lose overlap between the two waveforms, then you lose signal to noise, and eventually you are going to miss some signals. And how much of a mismatch between those waveforms you allow is a bit of an arbitrary decision. It has to do with how willing you are to lose signals in LIGO. And the criteria that has been used by the LIGO collaboration for a while now is saying, okay, we are willing to lose about 10% of our signals due to poor waveform modeling. And so because the number of signal loss goes like the cube of the lost signal to noise because LIGO is sensitive to a certain volume, you say, I want the overlap between waveforms to be at least 97%. And there's a mathematical definition of that, but it's more complicated. So that's the criteria that you want for detection, and that means that the 10% weakest source might be lost. And so when LIGO constructs its template bank, its list of waveforms that it's comparing the signal to, it's trying to make sure that any real signal that might arrive matches one of the templates to at least 97%. That decides both the accuracy required for numerical waveforms and also how many templates you actually need. Right? If you are willing to have templates that don't match a signal that well, you can have a smaller number of waveforms that you compare to. And comparing waveforms to the signal is expensive, so you don't want to have too many of them. So there is also a trade-off there. If you want to do parameter estimation measuring the masses and spins of the objects now, well, the criteria that you usually use is you would like the templates to introduce at most as much error as the detector noise so that you're not dominated by your theoretical uncertainty. Mostly because it's a lot cheaper to do numerical simulations than to build LIGO. So you don't want LIGO to be limited by numerical simulations. It would be a waste of money. And to do that, what you need from the numerical simulations depend a lot on the signal, because that becomes harder to do as the signal becomes louder. If you have a louder signal, your uncertainty from the observations becomes smaller, and so you need the numerical simulations to actually be of higher accuracy to be sure that they do not dominate the error budget. And currently, from recent estimates of the accuracy of numerical waveforms, we think that we are okay up to signal to noise in LIGO of about 30 to 50, so something around there. It depends a lot on the parameters of the binary, but for the kind of things that LIGO sees. And the loudest event in LIGO was a signal to noise of 24. So at the moment, numerical simulations are still ahead of what they need to be, but the sensitivity of LIGO is going to improve by about a factor of 2 in the next few years. And then we start to reach a regime in which maybe we need simulations that are and models that are a little bit more accurate. So there's still work to do. And because the signal to noise of binaries in LISA is much higher than in LIGO, For LISA, you need much more accurate waveform. And that's a significant issue. Is getting from what we currently have to what LIGO will need at design sensitivity. That's just doing slightly more accurate simulations with the code that we already have. It's not easy, but there is a clear path forward. Getting to the accuracy that LISA needs, that's orders of magnitude more accurate. And so there we actually need to think carefully about how we are going to do that. That's a much more significant challenge. Okay, and the other motivation to do numerical relativity, which will be more, which will be described more in the later lectures, is to actually model the electromagnetic signal that comes from binary mergers. Not black hole mergers in this case, but neutron star, and neutron star black hole mergers. And we see that there is a wide range of electromagnetic signals, and we already have heard some of that from Ariadna's talk on Wednesday. So we want to be able to model the gamma rays, X-rays, kilonova in optical and infrared emission, and the radio emission that comes from these systems. And we'll see a little bit of that this afternoon and probably Monday. Okay. And you also get a lot more information about the observations themselves from Samaya's talks sometime next week. I don't remember when exactly. Right. And then numerical relativity is not only used for compact binary mergers. It has also applications to other astrophysical systems. It's just that at the moment, people are very excited by compact binary mergers, so that's most of what we are doing. But you can also use the numerical relativity to do supernova explosions. In supernova, general relativity is not the leading order effect in your determination of the explosion mechanism, but it actually does play an important role. If you don't include general relativity, you do get errors in your predictions for which stars do explode and which stars do not. Not that the predictions from simulations are that great at the moment, but we know that there's at least a difference whether you use general relativity or not. And that's something that probably Philip will cover in his own lectures on supernovae. And you can also do things like accretion disk around supermassive black hole binaries in galactic centers, which is very interesting if you want to figure out what is the electromagnetic signal that will come from two black holes orbiting each other in the center of a galaxy. Which is something that we would like to know, because at the moment, even if we saw one of those supermassive black hole binaries, we would have a hard time proving that it actually is what we think it is. And so getting better prediction for what that signal should look like is an important objective if you want to figure that out. We think that there should be supermassive black hole binaries around us somewhere because they are a natural result of galaxy merging, but it's hard to prove for sure with current observations. There are candidates. So why is it hard to do numerical relativity? So all Einstein's equations first look are fairly easy. They can be written in one line. The curvature of space-time is equal to the matter sources, effectively. But any equation can be written in one line if you make your definitions complicated enough. And when it comes to general relativity, and I don't mean for you to actually understand every single one of those equations. The curvature of space-time particularly is a very complicated function of the metric, which is what we would like to evolve. And the thing to note here particularly is that so G mu nu is a rank 2 tensor, or a matrix if you prefer, a 4x4 matrix at each point in space-time. And it is a complicated function of all components of the metric. And it involves second derivative of the metric. So every time there is a comma in this definition, it's a derivative. That's the way general relativists typically write derivatives. And you see that there is a first derivative of the metric in the definition of that gamma parameter, a second one in the definition of the Riemann tensor, and then so you have mixed second derivative of the metric of all components of the metric, which are mixed together in each of the component of G mu nu. So because G is symmetric, that's 10 coupled nonlinear equations involving second order derivative of the metric, involving both spatial and time derivatives of the metric, assuming even that you know what spatial and time means in general relativity, which is not an easy question itself. So one of the first challenge for numerical relativity is to actually take these complicated equations and write them in a way that you can evolve them on a computer. What you would want is go from that mess of time and space derivative coupled together to a problem in which you can have initial data on a given time slice at a given time, and then evolve it with a unique solution into the future. That's how you normally think about the numerical simulations, but that's not what these equations give you at the moment. You need to actually figure out how you are going to go from Einstein's equations to a time evolution with a meaningful definition of time evolution. That's complicated, and it took a long time for people to figure it out. The basic idea, at least to get to the time evolution part, is the so-called 3+1 formalism decomposition, or ADM for Arnold, Dessner, and Misner. And that's saying, well, okay, I have that four-dimensional space-time, and Einstein's equations are very nice because they treat space and time as the same thing, and blah, blah, blah. It's nice. But it's very bad for numerical simulations. We don't want to treat space and time as the same thing. We want to treat space and then evolve in time. And so what we do is we take that beautiful theory and we cut it. We cut space-time in three-dimensional slices, which are spatial slices, and we annotate each slice by a certain time. That time at this point doesn't mean anything. It's just annotating the different slices. Okay, and then in each of those slices, which is three-dimensional, we define a three-dimensional coordinate system. And the problem is that we can do that in an infinite number of ways. It's entirely arbitrary what I do there. And so there is, for example, no guarantee that what I define as time, which would be the vector, linking points with the same spatial coordinates on two different slices, is in the same direction as is even orthogonal to the spatial slice, like you would normally expect. So there is going to be a shift between what an observer, which is at constant coordinates, does in your spacetime, and what an observer which moves normal to the slice does in your spacetime. So the normal here is n, right? And the time direction is that delta t here on the right. And so there is a shift between the two, which is called the shift beta. And at the same time, even if I was following the normal, even if I was going orthogonal to my slice, because I have arbitrarily decided what time means, there is no guarantee that if I had a clock and I was counting the time it takes me to go from slice A to slice B, it corresponds to the difference in the time coordinate that I have arbitrarily set. And so there is another correction which has to be made to the definition of time here, which is the lapse, which tells you how much time an observer going around the normal would actually see in practice. If it was, if it was measuring time on an actual clock, it wouldn't see the difference between the time markers of those slides. It would see alpha times that, so the lapse times that. So that tells you how much real time passes between slices and how much observers following the coordinates shift compared to someone who would go normal to the slice. All right, and with that at hand, now you can actually write evolution equations. And because Einstein's equations are second order, you need to first define an extra variable, which is basically the time derivative of the metric. If you have done some differential geometry, it's the Lie derivative of the metric along the normal direction. But basically, it's the derivative of the metric along the normal. That's called the extrinsic curvature. It tells you how your slices are curved in the full four-dimensional space. And once you have those, you can actually write evolution equations for the metric of the three-dimensional slices and that extrinsic curvature. So that is something that you could, in theory, put on a computer. It tells me the time derivative of the metric and of the extrinsic curvature is something which only depends on the values of these quantities on the slice. So I can actually do that on a computer. That's not all of the equations in Einstein's equations of general relativity. There are also constraints which have to be satisfied on each slice, which are complicated function of the metric and extrinsic curvature. It's generally, it's quite common at least to do to draw a similarity between the equations of general relativity and the equations of electromagnetism. It's easier to think about electromagnetism because the equations are simpler and there are less components, and also we have some intuition of how electromagnetism works. The evolution equations of general relativity can be compared to the evolution equations of the electric and magnetic fields in this case, vacuum electromagnetism. I'm not going to start with D and H here. And the constraints are similar to the divergence equations in Maxwell's equations for electromagnetism. So divergence C should be the charge density, and divergence B should be 0. And that also has to be satisfied at each time in electromagnetism, in the same way that these constraints in general relativity have to be satisfied at each time. Right. And so the problem that we have to solve with that 3+1 formalism now is, well, the first one is, how do we choose that foliation of spacetime? How do we choose the slices and the coordinates within the slices? It's not an easy question. I mean, if I have a single black hole and I know analytically the solution, I can figure out a good coordinate system at any time because I already know the solution. But for a binary system where I don't know my spacetime is going to evolve, how do I a priori define what those slices should be and where those coordinates should go? Because I don't know what my spacetime will be in the future. So you end up with a requirement to write evolution equations, or at least to choose on the fly what those laps and shifts are. And it's not intuitive what that choice should be. And that's one of the things that tripped people up for the longest time is, how do you actually make that choice if you don't know what your system is going to look like in the future? The other one is that in electromagnetism and in general relativity both, if I start from initial conditions that satisfy the constraint and I evolve exactly the equations, they continue to satisfy the constraint. It's necessary if you want your equations to be self-consistent. But there is absolutely no guarantee that if I start with a small error in the constraints, or if I introduce one by numerical error in my evolutions, those errors are going to remain small. And in fact, in the standard formulation of Einstein's equations, and also in some cases for some formulation of electromagnetism, those errors can grow pretty fast. Those errors can grow exponentially. And quickly you end up with a solution which is mostly constraint violation and doesn't mean anything anymore. It's out of the subset of solution that is physically acceptable. So that is a big problem, and that's one that numerical relativity had to solve. One that I will not be discussing, but that is very important to do realistic simulations, is how do you even choose your initial conditions in general relativity? Yeah. And how do you get a formulation of the equations which is well posed, meaning that it's going to be evolving stably and it lead to a unique solution? And finally, what do you deal with singularities? You have black holes. You're trying to evolve black holes. Black holes have a singularity. Singularities are not good for numerical simulations. So how do you make sure that you avoid having your numerical simulations run into those infinities at the black hole and blow up? That is actually related to the question of the choice of lapse and shift, and that was one of the main roadblocks to get simulations of binary black holes to work in general relativity. Okay. So as I only have 3 minutes left, I think that I'm going to leave the answer to those questions for this afternoon. Or rather than do only one of the questions and stop in the middle. So if there is any other questions on that, or on LISA or LIGO and black hole detections, I'm going to take them now, and otherwise we can have a break that is 2 minutes longer for coffee.
What's the proposed lifetime for
the proposed launch date currently is 2034. And there is, so that's the current plan by the European Space Agency. It has reserved one of its flagship missions part for LISA. That, like everything that has to do with satellite launch, it can easily change due to a large number of potential issues. So there is no guarantee that that's when it's going to be, but that's the current plan, 2034. Oh, that's a good question. I think it's sort of the order of 5 to 10 years, but I'm not sure. I can check the proposal and get back to you on that. As I say, my knowledge of LISA is fairly limited.
Maybe not the best question for this room, but is most of the cost associated to the launch or to the building of the spacecraft? Because I've seen many interesting proposals about the science we could do with if we had N LISAs. So like a constellation of 6 LISAs, for example. And so I'm wondering if with like SpaceX driving down the cost of launches, we can dream about doing this.
So the launch is definitely a large component of the cost, a very large component of the cost. Because I know that when they were trying to reduce the cost of LISA, one of the main proposals was to go from 3 launch vehicles to 2 and have, you have those 3 satellites, and instead of having 3 big satellites, you would have 1 full and 2 halves, and the 2 halves would be launched in the same, and that was seriously reducing the cost. And I don't think the technology would not have been that different. So it's clearly an important part of the cost. SpaceX is capable of launching something in orbit, but they don't have the technology yet to go in orbit around the sun, a month behind the Earth. That's something so far that maybe they will, I don't know, but I don't think that's in the at least announced plans in the next 10 years. And they will have to demonstrate that they have the technology to do that, right? So it's a much more difficult launch than going into orbit around the Earth. You're trying to launch yourself in orbit a month behind the Earth around the sun, and on a very, very, very well-defined orbit, because the whole point is that you are trying to measure very accurately the position of these spacecraft. So it's a very difficult launch to make. Yes? Do you have a question?
3 plus 1, but maybe.
Yes.
Please.
Then those red curves in the LISA plot that correspond to extreme ratio mergers, do they cover the conventional tensor destruction events we know, or you need something more heavy to merge with the black hole?
Okay. So the standard tidal disruption event is a nearly parabolic orbit. It's a very high eccentricity orbit. These are more circular orbits. So I mean, a standard tidal disruption event, because it disrupts actually very close to the black hole, is not that different from a black hole or a neutron star getting close to the black hole on the same orbit. Only the very end changes. But these rely on multiple, many orbits around the black hole of a single object, where a TD is basically one passage and you disrupt. So there's not much signal in there. Right? Right.
But the final stages, maybe?
The final stage of
The tidal disruption event? You could guess
well,
the horizon?
So if you had something, if you had one solar mass star that does not disrupt and plunge into the black hole, I mean that part would look nearly identical, yes, to the single object. But again, it's a single passage. You don't accumulate much signal. It's one star coming from far away, coming close to the black hole and plunging into the black hole. These MRIs are one object doing millions of orbits around the black hole. It's
What how can you make such a red curve?
So the idea is, yeah, you have one black hole or neutron star which goes 100,000 million orbits around the black hole very slowly in spiraling, because the gravitational wave emission is actually a small effect in those high mass ratios systems. So it does many orbits relatively close to the black hole already in a nearly circular orbit, and accumulate signals over all that time. And that's what those are supposed to be. It's not one passage of a very eccentric system.